Welcome back, Seth Bling here. I wanted to make a video showing you what it took to make my Minecraft physics engine data pack. I saved copies of the data pack as I worked on it, so I'll show you every step from absolutely nothing to a working physics engine. This physics engine is basically an implementation of the book Game Physics Engine Development by Ian Millington, and most of my journey mirrors the chapters in that book. This is the very first version of the data pack. It had been years since my last Minecraft data pack, so first I just needed to make sure I still remembered how to use my CV script compiler. Display entities were also new to me, and I needed to learn how to set the transform matrix, which was going to be crucial to this project. With the proof of concept done, the next step was to implement quaternions to represent orientation. Quaternions are a complicated mathematical concept. They're basically four-dimensional extension of the complex numbers. I'm not going to go over how they work, but I can tell you that they're really important for representing orientations of three-dimensional objects. Here I'm using a quaternion multiplication to rotate the cube around the axis. The next step was to implement transforms between world coordinates and local coordinates, and use that to implement ray intersections. World coordinates are how we normally think of x, y, and z coordinates when walking around a Minecraft world. Local coordinates are specific to each cube, such that the origin is in the middle of the block, and the block is in a fixed axis-aligned orientation like this static Minecraft block. In order to make this cursor intersection work, I created a ray with its origin at my eyes and pointed in the direction I'm facing, and then I transformed that ray into this cube's local coordinates, which were constantly changing, so that I could test if the ray passed through the unit cube at the origin. This next step wasn't really necessary for the physics engine, but it's a good demonstration of what a normal means in 3D geometry. This line of bubbles is always pointing directly away from the face of the cube. That's called a normal. It's just a vector that's perpendicular to a plane. Normals are really important for figuring out how things should bounce off of each other. Next, I implemented impulsive torque. Basically, by hitting a cube away from its center point, that imparts some rotational velocity. The farther away from the center, the faster it'll spin. This was the first bit of physics I implemented, and I started here to make sure that I had a good grasp of rotation before proceeding. Next, I wanted to implement translational physics, that is, movement horizontally and vertically, but I didn't want to implement collisions yet, so I decided to implement a spring cable. This allowed me to see an object moving around believably and responding to impulses without implementing a full collision engine. Finally, with the basic impulse physics out of the way, it was time to start implementing collisions. I started with the simplest thing, which is a single infinitely large ground collision plane. This is a hard-coded plane with its normal pointing directly upward. Basically, we can test each corner of the cube to see if it's on the wrong side of the plane, and if it is, then there's a collision. However, at this point, I realized something was wrong. I was getting very buggy behavior. Sometimes the cube would just rest on an edge. I wasn't sure what was causing it, and I spent 2 full days debugging it before I figured out that it was the result of some sign errors in the physics textbook I was using. It was really difficult to pin down that bug. I didn't know if it was caused by a faulty collision engine, a bad physics implementation, a bug in my CB script compiler. I had no idea. The textbook formula is really the last place I thought to look for an error, and this was definitely the closest I came to giving up on this project. With that fixed, things started to look pretty good. I will say that I didn't follow the book's implementation of friction at this point, and instead guessed at how it should be implemented, and honestly, I think it looks pretty good despite just sort of making up the math. Here's what it looked like once I implemented the real friction computations that the textbook laid out, and it definitely looks a little less chonky. At this point, the physics engine was pretty much complete for a single collider, and this really doesn't look any different than the final version if you just have a single cube on a super flat world. From here on, the challenge was to implement more types of collisions. The next step was to take my hard-coded ground collision plane and generalize it into planes in other directions. So I added wall planes. This step also introduced multi-step collision resolution, since a cube might be in contact with multiple planes at a time, and you need to resolve all of them in a single time step. Now that I had collisions in arbitrary directions, it was time to implement collisions with world geometry, that is, Minecraft blocks. At first, I only implemented collisions between corners and faces, leaving edge-edge collisions for later. Most of the time this actually looks pretty good, and you can see the cube collides just fine with these little structures I built. However, if a cube comes to rest in a bowl like this, you can very easily see where edge-edge collisions become apparent. Still, even in these cases, the corners of the blocks and the cubes keep things from interpenetrating too deeply. At this point, the physics engine was starting to take up a lot more computing power. If you have a large cube like this one, it has to do a lot of checks for collisions with blocks. So at this point, I implemented a sleeping system. Basically, if a cube is moving slowly enough for long enough, it goes to sleep and the physics engine stops simulating it until it's hit by something. This allows there to be a lot more colliders spawned at a time, as long as some of them aren't moving. The next step was collisions between the edges of colliders and the edges of Minecraft blocks, and it's really where my geometric intuition started to break down. So to start, I implemented ray marching along the edges of the colliders, marking where the edge passes between the cells of the Minecraft world grid that all of the Minecraft voxels are aligned to. If I turn on the chunk boundaries, you can see that all these points line up with the grid boundaries. Next, using the edge traversal, I detected where the edge of a collider intersected a Minecraft block and added some smoke particles. This let me know that I was correctly detecting the places that there should be edge-edge collisions. The final step before actually resolving edge-edge collisions was to figure out which edge of the Minecraft block was penetrating the cube, and so I used these lines of bubble particles to mark those. Now that I knew which edges of the cubes were penetrating which edges of the blocks, I was ready to implement edge-edge collision resolution. Here you can see my first implementation of that. You can still see the lines of bubbles momentarily until the collider goes to sleep. You'll notice that the cube no longer interpenetrates the block along the edges and instead rests on the edge. At this point, collisions between colliders and the world geometry was complete, although it was still a little bit buggy. Next, I got to work on making colliders collide with each other. I started out with corner face collisions, just like for world blocks. At this point, I had to implement the last bit of physics as well, which is to make two colliders bounce off of each other correctly. You have to take into account the relative masses and rotational inertias of the cubes, their relative velocity at the collision point, and a few other things. But with that done, the cubes could bounce off of each other. Finally, I implemented edge-edge collisions between colliders. With this done, I considered my physics engine feature complete, even though it still had some glitchy looking behavior now and then, and the performance can still use a bit of improvement. At this point, I wanted to make something fun, so I brought back the spring cable from the beginning of the video and made tetherball, but this time with a pole in the middle that the cube could actually collide with, though of course the tether didn't wrap around the pole. In order to take on some of the glitchy behavior I was seeing, I implemented save states. They allowed me to debug exactly what was going on during glitchy behavior. I could freeze the game and inspect all of the data in the engine. I could even recompile in some debug messages to figure out why the code was doing what it was doing. The final big change was to use the separating axis theorem to make the collisions a bit more reliable and less glitchy looking. The separating axis theorem basically says that if two cubes aren't touching, then there must be some axis and some plane normal to that axis that separates the two cubes. Conversely, if they are touching, then there isn't any plane that can be used to separate the cubes. There's a specific set of 15 axes you can check, which are the normals of the faces of each cube, as well as the 9 cross products of those normals between the cubes. And if there is separation on any of those axes, then the cubes aren't colliding. And if there aren't any axes that have separation, then the cubes are colliding. With the separating axis theorem implemented in my collision engine, it was finally complete, and this is pretty much the version I released. It took about 6 weeks to complete this project, and it was one of the hardest things I've ever done. I almost gave up a couple times, but I'm really glad I didn't because in the end, I learned so much and ended up with something really cool. Hopefully you learned a thing or two as well. That's about it. Thanks for watching.